Hi, my name is John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. On this particular video, we're going to talk about the chain rule for differentiation. Let's start. The chain rule, in my opinion, is one of the most powerful, one of the most important rules in differentiation. Okay, so it's very important to first understand when to use it. Okay, to identify when do we actually use the chain rule. That becomes the first important thing. So let me explain that using a very simple example. So I'm just going to write down chain rule, and let's take one simple example. Okay, so when you have a function like tan of x, okay, a standard function y equals tan of x, the derivative dy by dx we know is secant square x with respect to x. Okay, so when y is given as tan of x, the derivative of tan of x with respect to x is secant square x. You can't use this rule directly if it were a composite function. So if you had, instead of y equals tan x, let's say you have y is equal to tan of 3x. There, if you were to find the derivative of tan of 3x using this rule, you can't say that it is secant square 3x. That would be not fully correct. It's incomplete. Okay, that's because this is a composite function. It's not the standard function tan of x. So if you're differentiating y is equal to tan of 3x, the composite function tan of 3x, then the derivative dy by dx is not going to be equal to secant square x 3x. You can't use this rule directly. Okay, there's a rule for the composite functions, and that rule is what we are calling the chain rule. So the first thing we want to make a note of is this chain rule is for composite functions. Of course, you can have much more complicated composite functions. This is a very simple example, but let's use a simple example to understand how we use the chain rules. First, how we spot that it's a composite function. So tan of 3x is a composite function. You can't use the same rule, the standard rule, which is tan, the derivative of tan is secant square. You can't use that. That's the first thing to note, okay? So other examples would be something like, if you had, using the same idea, if you had y is equal to, let's say, tan of, let's say, square root of x, or if you had a function which says tan, the square root of tan of x. These are all examples of the composite function. Okay, it looks the same. This is a standard rule. This is a standard rule. The rule that you used for tan of x, okay, y is equal to tan of x, the dy by dx is secant square x. That rule cannot be directly used when you have a composite of the tan. Okay, it's like tan of 3x or tan of root of x or the square root of tan of x. So let's try and understand how we use it. The first thing I just said, let's identify what makes that a composite function. So these are all examples of the composite function. And we already seen before, let's take the example of tan of 3x. What is a composite function? Well, a composite function actually has two domains. Okay, the first thing is going to take x, the input, the first input, let's call this the domain 1, takes it to a range, let's call that range 2, range 1. It will go, all the x's are becoming 3x. And then we have tan of this new domain, which is the range 1. Okay, so that becomes range 2. Okay, and so that becomes tan of 3x. So it's literally like combining two domains. This is the first domain, this is the second domain. The second domain is where we are operating tan, not on x. Okay, so it's not tan of x, it's tan of 3x. So x is going to 3x and then finding the tan of 3 of x. If you recall from that video on composite functions, we use the word inside function and an outside function. It's a function of a function. That is how we define composite functions in that video. I'm going to link that video in the description box below. If you've not seen that video before, you must go and take a look at it, okay? The inside function in this case is this first function, okay? That's what 3 of x is. The range of that inside function becomes the domain or the outside function, okay? That's important to know. So what we're going to do is that we are going to call that inside function u. So let me just do that example again. This is going to be example 1, where f of x, which is y, is tan of 3 of x. Okay, I'm going to put that into the bracket. That's the inside function. That inside function, I'm going to call it u. So it literally is f of x is tan of u. All right, so that inside function, if you can identify the inside function and say that is going to be our u, then the derivative according to chain rule is going to be something like this. Dy over dx, okay, or f prime of x, whichever notation you're using, you can even call it f prime of x. Remember, this derivative is with respect to x, okay? So what we're going to do is that we're going to find the derivative of the outside function, okay? The outside was tan outside was tan, all right? So the derivative of the outside function, which is secant square u, multiplied by the derivative of the inside function, which is du over dx. So what did we do? We found the derivative of the outside function, okay? The outside was tan, the inside was 3x, okay? So the derivative of the outside function, tan of u, that looks very similar to the general rule that we had, the standard rule, right? So it's reducing it to the general rule, the standard rule. We can say that's the derivative of the outside function, which is secant square u. But that inside function, u itself is another function. That's why it's a function of a function, right? So the derivative of the outside function, secant square u, and the derivative of that inside function, du by dx, u is equal to 3x, right? The derivative of that inside function is going to be 3 because they were using, the power rule, x to the power of 1, and 3 is just a constant multiple of that. So this term is just going to be 3. And here we've got secant square. I'll bring back my u, which was 3x. So the final answer can be written as 3 times secant square 3x. Okay, that is going to be by dy over dx. Let's go with this rule again. This is chain rule, by the way. Okay, so how did we do it? The derivative is basically, if I were to write it down as dy by dx is derivative of outside function. And when we say derivative of outside function, what needs to be kept the same is inside function remains unchanged. Okay, multiplied by derivative of inside function. Okay, so that is the chain rule. Okay, so what happens is you're finding, because you have f of g of x, right? So if I say y is given as f of g of x, you need to first identify what is our inside function. The inside function is g of x, okay? So you're basically finding the derivative of the outside function. That means the derivative of f inside remains unchanged. That's important, okay? Multiplied by the derivative of the inside function, which is the derivative of g, okay? So if I were to write it down, it would simply mean f prime of g of x multiplied by g prime of x. This is the chain rule. Let's recall that rule quickly. This is the chain rule. It's for composite functions. So the composite function is of the kind f of g of x. You have an outside function, you have an inside function, and you can have different layers also. You can have more than 2 layers, okay? So if it was 2 layers, we saw that you first find the derivative of the outermost function. Outermost function when the inside function remains unchanged. That's important. Multiplied by the derivative of the inside function. If there were many more layers, you go from starting from the outermost first and go in the same fashion to the innermost function, okay? With more practice, you'll get a hang of this chain rule. Like I said at the start, this is one of the most powerful, one of the most important rules in differential calculus. The most important thing being to identify when to use the chain rule. If you found this video useful, please make sure that you like, share, and subscribe to this channel. I'm going to see you all in the next video.